Hi friends, welcome to my YouTube channel. My name is Darun M. I'm studying in Sri Venkateshwara College of Engineering. Today we are going to discuss about engineering mathematics. In that first module is differential calculus. In that we are going to discuss about polar equation of a polar curve. Introduction to polar coordinates content. Polar coordinates are a different way to representing points in a plane compared to the more familiar Cartesian coordinates x, y. Instead of using horizontal and vertical distance, polar coordinates are used to distance or from a fixed point and an angle theta measured from a reference direction, usually the positively x-axis. In the polar coordinates, a point is denoted as r, theta when r represents the radial distance from the origin to the point and theta represents the angle formed with the reference direction. Polar coordinates are partially useful for describing points that have radial symmetry, such as circles, spirals, and curves that emanate from a central point. They find application in various fields, including physics, engineering, and mathematics, or complex geometries and circular patterns are common. This presentation will develop into concept of a pedal equation of polar curves, which allows to explore the relationship between polar curves and pedal curves generated by dropping perpendiculars from a fixed point into the original curve. Polar coordinates. Polar coordinates an alternative coordinate system used to describe the position of points in a two-dimensional plane. Unlike Cartesian coordinates x, y, which uses horizontally and vertically distance from a fixed origin, polar coordinate uses a different approach. A point in a polar coordinate is defined by two values, the radial distance r and the angle theta. The radial distance r represents how far the point is from the origin, also known as the pole. The angle theta represents the counterclockwise rotation from a reference direction, typically the positive x-axis. The point is denoted as r, theta, where r is non-negative real number and theta is typically measured in radians. Polar coordinates are especially useful for describing any analyzing patterns and shapes with radial symmetry, such as circles, spirals, and many types of functions. Understanding polar curve is essential for exploring the pedal equation of polar curves, which is focus of this presentation. Polar curves. Polar curves are a class of mathematical curves represented in polar coordinates which consist of a radial distance r and an angle theta. Unlike Cartesian curves which are expressed as a function of x and y, polar curves describe the relation between r and theta. Polar curves are commonly used to represent patterns and shapes that have radial symmetry or more naturally expressed in a polar coordinate system. Common example of polar curve includes circles r is equals to constant, coordinates r is equals to a 1 plus cos theta, spirals r is equals to a theta, lemni sectors r to the power of 2 and a to the power of 2 into cos 2 theta. Polar curve, often having visual appealing, the geometrical intersecting shapes making the fantastic subject of study in the maths and science. In this presentation, we will explore a mathematical tool that helps us understanding polar curve better. The polar equation. The polar equation allows us to analyze the relationship between polar curves and their pedal curves. Pedal equation of polar curve. Define pedal point and the fixed curve. The pedal point is typically a point on the moving curve. The fixed curve remains stationary. A pedal curve is the path traced by a point called the pedal point on a curve as it rolls along the outside of another fixed curve. The pedal equation from a polar curve is the way to describe the pedal curve that results from tracking the path of a fixed point on the original polar curve as it rolls along the outside of the another fixed polar curve. The pedal equation is derived based on the geometry of the curve involved. The equation describes how the pedal curve is found by tracing the path of the pedal point on the original polar curve as it rolls along the outside of another fixed polar curve. It is important to note that the pedal equation depends on a specific form of the original polar curve f of theta and the location of pedal point alpha. The pedal curve can exhibit various interesting shapes and patterns depending on these parameters. When alpha is equal to 0, the pedal point is on the positive x-axis and the equation Rp is equals to cos of theta by f of theta. The pedal curve. The pedal curve is mathematical concept related to polar curves which provide insights into the relationship between polar curves and a fixed point called the pole. The create a pedal curve. We start when given polar curve from each point on the curve. We drop a perpendicular line to a fixed point known as the pole. The resulting collection of the feet of these perpendiculars traces out a new curve known as pedal curve. The pole is critically element in this process as its location influence on the shape and characteristics of the pedal curve. The pedal curve helps us understanding how points on the original polar curve related to the pole and how their position change when projected into the polar curve. This concept is not only mathematically interesting but also has practical applications in the field like physics and engineering for understanding circular and radial patterns. In this presentation, we will delve into the mathematical formulation of the pedal equation and explore its significance in analysis polar curves and their pedal counterparts. Pedal equation formula. The pedal equation is a mathematical formula that depends the relationship between a given polar curve and its associated pedal curve. In this equation, r of theta represent the distance from the pole to a point x, y on the pedal curve. X and y are the Cartesian coordinate of the foot of the perpendicular dropped from the pole to a point on the original polar curve. The pedal equation provides a way to calculate the radial distance from the pole to each point on the pedal curve based on the coordinates of the foot of perpendicular from the pole, the origin curve. Understanding the pedal equation allows to explore analyzing the geometric properties and relation between polar curve and their pedal counterparts. In the following slides, we will walk through how to calculate the polar curve as given polar curve and explore some real-world application of mathematical concept. Calculating the polar curve. Now that we have introduced the pedal equation, let's explore how to calculate the pedal curve for a given polar equation. To calculate the polar curve, follow these steps. Choose a polar curve with an equation r comma theta that describes into shape and size. Determine the coordinate x comma y of the foot of the perpendicular dropped from the pole of each point on the original curve. This can be done by using properties of polar coordinates and trigonometry. Apply pedal equation Rp of theta is equals to r power 2 into y power 2 to find the distance from the pole to each point on the pedal curve. Plot the resulting points to create the pedal curve. Properties and application. The pedal equation of polar curve has several interesting properties and particles. Properties. First one, symmetry. The pedal curve is symmetry with respect to the polar curve. This means that if the original curve exhibits certain symmetry, those symmetries are preserved in the pedal curve. Location of the pole. The choice of the pole's location can significantly affect the shape and characteristics of pedal curve. Different poles location widely different pedal curves. Special cases. Some pedal curves exhibit intriguing properties such as loops, curves, and self-interactions depending on the original curve's equation. Applications. First one, mathematics. The pedal equation is valuable tool for studying polar curves and their properties, allowing mathematicians to explore relation and pattern with curves. Second one, physics. In physics, the concept of the pedal curve is useful for understanding orbits, especially in the involving central process. It flows into how an object's trajectory change corner of center. Engineering. The pedal equation can be applied to analyze the paths of mechanical linkage structure pattern generated by rotating machinery. Geometric. The pedal equation is fundamental concept in geometric analysis, offering a way to investigate the shapes and transform of polar curves. Summary. To summarize, in this presentation, we have explored the concept of pedal equation of polar curves and signature and significance. We began by introducing polar coordinates, a different way to represent points in a two-dimensional plane using radial distance and angles. When they developed into a notation of polar curves which describe the relation between these coordinates, often showcasing radial symmetry. The pedal curve, as a fantastic mathematical construction, is generated by dropping perpendiculars from a fixed point, the pole, to a given polar curve. We discussed the pedal equation formula, or P of theta is equals to r to the power of 2 plus y to the power 2, which relates the polar curve to its pedal curve. We also explore the properties of particular applications of pedal equation analyzing planetary orbits and mechanical linkages to design robotics, even a artistic creation. Understanding the pedal equation provide valuable insight into the geometrical and behavior of polar curves in the different fields.